Welcome back to the Deep Dive. Today we're looking at something all around us, literally. The glass in our windows, our phone screens, even soda bottles. We're going to uncover the pretty amazing journey from simple sand to this transparent, durable material.
It's funny, isn't it? We think of glass as modern, but it's ancient. It wasn't really invented, more discovered. Like over 2,000 years ago, apparently Egyptians heating silica sand and sodium carbonate near a fire just stumbled upon it. An accident.
Wow, a total accident that changed everything. And we often think, glass, it's fragile, it shatters. But industrially, it's tough stuff. Resists heat, electricity, and the recycling part is incredible.
Absolutely. That it can be recycled 100% over and over with no loss of quality, that's huge for sustainability.
Definitely.
But our mission today really is to dive into the making of it, the sheer scale. We're talking millions of tons of material. And the process starts, well, surprisingly violently, actually, and ends with mind-boggling precision.
Okay, let's get into it. It starts with sand. But you mentioned it's not the kind of sand you find on a beach, right? What's the difference?
Yeah, exactly. Beach sand, desert sand, it's got too much other stuff in it, impurities. For good quality glass, you need silica sand that's almost perfectly pure silica, like 99% pure.
99%.
Okay.
So you can't just shovel that up anywhere. Where does this super sand come from?
It's mined from these huge open pit mines. The silica isn't loose sand there. It's locked up in really dense rock layers. And here's the first kind of shocker in the process. They use industrial explosives to get it out.
Wait, explosives? To make something we think of as delicate, like glass?
Believe it or not, yeah. They have to shatter these massive rock formations to access the silica-rich stuff. It's pretty dramatic.
Definitely not what I pictured.
Oh,
Okay,
yeah.
so after the explosion,
Then the big machines move in, giant excavators scoop up all that shattered rock, and they haul it off to crushing facilities. Think powerful industrial mills that just grind and grind that rock down. The goal is to get uniform, fine granules. Like sand, but engineered sand, you could say. Particle size has to be consistent.
right, consistency is key. So, okay, we have crushed rock, basically superfine engineered sand, but you said purity is vital. It's still not pure enough yet.
Not even close, usually. That's where the next stage comes in this massive industrial washing process. Some plants can wash like 220 tons of this stuff per hour.
220 tons an hour. That's like a giant laundry for sand. Why such intense cleaning? What are they getting rid of?
It's all about clarity and strength. Even tiny, tiny traces of metals, especially iron, can mess things up. Iron gives glass that greenish tint, and other impurities can weaken it or cause bubbles. For crystal clear, strong glass, it has to be spotless.
Got it. So how do they actually wash it? Is it just water?
Well, first, there's basic sieving, like using really fine nets, maybe 30 holes per square inch, just to filter out any slightly larger bits that survived the crushing.
Okay, screening first.
Then the fine grains go into these vibrating rooms, and yeah, they get blasted with high-pressure water jets for about 15 minutes. Workers there apparently describe the jets as feeling like needles, so it's intense scrubbing power.
Wow, needles of water. That's serious.
Definitely. After that, the water and sand slurry flows into a spiral separation system. This part's clever physics. Instead of magnets, mostly, they use centrifugal force. As the mix spirals down, the heavier stuff, the metal particles, gets flung outwards.
Ah, so it separates by weight. Heavier impurities out, lighter silica stays in the main flow.
Exactly. It's a really effective way to get rid of those heavier contaminants.
Makes sense.
Though, just to be sure, there's often a final mechanical separation unit specifically designed to grab any last microscopic traces of iron that might have sneaked through.
Super thorough.
Totally. And once it's all washed and dried, this ultra-pure sand gets packed into huge 1-ton bags. And just to give you a sense of scale again, a big glass factory in the U.S. might go through over 5,000 tons of this purified silica sand every single week.
5,000 tons every week of sand that started as rock, blown up in a mine, and then got put through the world's most intense car wash.
Okay.
So now we have the base ingredient, ultra-pure silica sand. But sand needs incredible heat to melt, right? Like thousands of degrees.
Yeah.
How do they manage that? Is there a trick?
There is. This is where the recipe comes in. You don't just melt pure silica, you add other things. The most crucial additive is sodium carbonate, often called soda ash. It acts as a flux.
A flux, what does that do?
Basically, it messes with the silica's molecular structure in a way that significantly lowers its melting point. Makes it easier to melt and blend. So instead of needing, say, over 1700 Celsius just for silica, adding sodium carbonate brings that down considerably. Saves a huge amount of energy.
Ah, okay. So sodium carbonate is the energy saver. Smart. What else goes into the mix?
Calcium carbonate, usually from limestone, is added too. That gives the final glass more hardness and stability, makes it less likely to dissolve in water, for example.
Hardness and stability, got it. And for colored glass, like blue bottles.
Yeah, that's when you add specific pigments,
Mm.
tiny amounts of metal oxides. Cobalt oxide is the classic one for that deep blue color. Other metals give you greens, browns, other shades.
Okay, so silica, sodium carbonate, calcium carbonate, maybe some color. They mix all this together.
Precisely. After a final filtration, everything gets transported on these big conveyor belts to a mixing area. High-speed mixers make sure every single grain is perfectly blended. You need that recipe to be totally uniform.
And then the furnace. This sounds like the really intense part.
It absolutely is. The mixture goes into a massive gas furnace, and the temperatures inside, they soar up to 1,650 degrees Celsius.
1650 C, that's over 3,000 Fahrenheit. Hotter than lava.
Hotter than most lava, yeah. It's an incredibly extreme environment. You hear about workers needing special heat-resistant suits, Kevlar gloves, face shields, just to do maintenance near it.
Wow. Is that temperature just unavoidable? Is it a physical limit for melting this stuff from scratch?
Pretty much, yeah. When you're starting with the raw materials, you need that intense heat to break down the crystalline structure of the silica and get everything to melt together properly. The mixture stays in there cooking for about 24 hours.
24 hours at lava temperatures.
Right, and after that time, it's not sand anymore. It's transformed into this thick, glowing, molten liquid, like incandescent honey almost. And it stays molten for even longer, several more hours, just to let any trapped gas bubbles escape. That ensures the final glass is perfectly clear and pure. No tiny imperfections.
Okay, so after more than a day, we have this perfect bubble-free liquid glass. Now we need to shape it. And you said the method depends on the product. Let's start with hollow things, like bottles or jars.
Right. For those, they typically use what's called the double blow method. It's incredibly precise. But even before the glass gets there, engineers have designed these super precise, heat-resistant metal molds using CAD software. Every dimension has to be perfect for, say, a soda bottle.
Okay, so the molds are ready. How does the liquid glass get in?
A stream of molten glass flows out, and it's cut into precise individual blobs. They call them gobs. These gobs are around 1100 Celsius, which is the ideal temperature, the right viscosity for shaping.
Gobs, okay.
Each gob drops into a primary mold. Then, stage 1, compressed air shoots in from the top. It pushes the gob against the mold walls, forming a kind of pre-shape. It's hollow, and it already has the neck finish of the bottle. This pre-shape is called the parison.
The parison, like a rough draft of the bottle.
Exactly, a glowing orange rough draft. Then, really quickly, that parison is transferred to the final mold, the one with the exact finished shape and any pattern.
And then stage 2.
Stage 2. Another blast of compressed air whoosh, pushes the parison outward so it expands and fills every nook and cranny of that final mold cavity.
And this all happens super fast, right?
Incredibly fast. The whole two-stage process, from gob to formed bottle, takes just seconds. It's all automated, controlled by sensors and valves, timed down to tiny fractions of a second. That's how they can make hundreds of thousands of bottles a day, all virtually identical.
Mind-blowing speed and precision, working with something that hot. Okay, so that's bottles. What about flat glass?
Yeah.
Windows, screens, solar panels.
Yeah, you can't blow those.
No, completely different approach. For flat glass, the magic is something called float technology.
Float technology. Sounds intriguing. How does that work? No molds.
No molds in the same way. Instead, the molten glass is poured out gently in a continuous ribbon onto a huge, perfectly flat surface of molten metal, usually tin.
A liquid glass onto liquid metal?
No.
Yep. Because the glass is less dense than the molten tin, it floats right on top. Like oil on water, but much hotter. And because of gravity and surface tension, the glass spreads out naturally into a perfectly uniform, flat sheet. The top surface is shaped by gravity. The bottom surface is shaped by the perfectly flat molten tin.
Wow. So the physics does the work of making it flat and parallel. That's ingenious.
It really is. You get these incredibly smooth, parallel surfaces without any grinding or polishing needed on the main faces.
And cooling must be critical here, too, to keep that perfect shape.
Oh, absolutely. As this continuous ribbon of glass floats along the tin bath and then moves off it onto rollers, it passes through different zones with carefully controlled temperatures. It has to cool slowly and evenly to prevent any stress or distortion from building up.
Once it's cool enough to be solid, how do they cut it?
Robotics take over. They use tools with diamond blades, sometimes lasers, to cut the still warm glass sheet into specific sizes. Very fast, very accurate.
And I imagine they polish the edges, Rock-cut glass is sharp.
They do. Abrasive wheels smooth and polish the edges and corners, partly for safety, partly for aesthetics.
Makes sense. And I read there's safety testing, especially for things like architectural glass or car windows.
Yes, definitely. Samples get put through impact resistance tests. Depending on the standard, like for car side windows, if it breaks, it has to shatter safely. You want that spiderweb pattern of small, relatively blunt pieces, not big, sharp, dangerous shards. That's a key safety feature.
Right, the safe shattering pattern. Okay, so whether it's a bottle that's been blown or a sheet that's been floated, it's formed. What happens next?
The final cooling stage, called annealing. Both bottles and flat sheets go through these long tunnels, often painted yellow, I think, to help manage heat radiation.
Annealing, is that just slow cooling?
Essentially, yes. The temperature is lowered very gradually, sometimes over minutes, sometimes much longer for thicker glass. This allows the internal structure of the glass to stabilize, relieving any internal stresses that built up during shaping and rapid cooling. If you don't anneal it properly, it could just spontaneously crack later on.
So it's crucial for long-term stability.
It's absolutely crucial. After annealing, the glass is stable, but it's not ready for packing yet. Next comes quality control, and it's intense.
How intense? Are people just looking at it?
Oh no, much more than that. It moves through this complex system of high-speed cameras, lasers, optical sensors, basically a high-tech inspection gauntlet. They scan every single item in real time, looking for any defect, a tiny crack, a bubble, a scratch, even a slight distortion in shape that you or I might miss.
And if it finds something?
Instantly flagged, and the defective piece is automatically kicked off the line. Only perfect items pass through.
That's incredible automation. So only the flawless glass makes it.
Only the flawless ones. Then, robots usually take over for packing. Using suction cups, they carefully stack the bottles or sheets, often putting protective layers in between. Then it all gets tightly wrapped in plastic onto pallets, ready to be shipped out.
Okay, so that's the journey from sand to finished product. But we touched on recycling earlier. How did that fit back into this whole flow?
It's not just an afterthought, it's deeply integrated, especially now. Remember all those pieces rejected by the quality control scanners?
Yeah.
They don't get thrown away, they get collected along with any other waste glass from the process and any glass returned for recycling from consumers or businesses. This broken glass is called cullet.
Cullet. Okay.
And this cullet is incredibly valuable. It gets crushed up and mixed right back in with the fresh batch of raw materials, the purified silica, the sodium carbonate.
So it goes back to the beginning into the furnace.
Exactly. And here's the really key benefit. Besides just reducing waste, cullet melts at a much lower temperature than the raw ingredients.
Oh, right, because it's already been glassed once.
Precisely. So by mixing in a good percentage of cullet, some factories use a very high percentage, they can significantly lower the temperature needed in that massive furnace.
And that's lower.
It can reduce the energy needed for melting by like 20 to 30%, sometimes even more depending on the amount of cullet used. That's a huge energy saving.
Wow, 20 to 30% energy reduction just by using recycled glass.
Yeah.
That's massive. So recycling isn't just good for the environment. It's actually a core part of making the whole process economically viable.
It absolutely is. It saves energy, reduces the need for raw materials, and cuts down on waste. It turns what used to be waste into essentially a fuel source for the furnace.
Oh,
It's
yeah.
a win-win-win.
What an amazing process we follow, seriously, from blowing up rocks in a mine
Yeah.
to washing sand with needles of water,
Yeah.
melting it hotter than lava, shaping it with microsecond precision,
Floating it on liquid metal.
inspecting it with lasers,
Yeah.
and then feeding the mistakes back into the start to save massive amounts of energy. It really is this incredible blend of brute force, high technology, and smart chemistry.
It truly is. And we saw how that initial melt needs that brutal 1650-degree heat when starting from pure raw materials. But then how mixing in recycled cullet drastically cuts the energy needed later on. It makes you think, doesn't it? As we need more and more specialized, ultra-pure glass for things like advanced touchscreens or complex optics, how will the industry keep balancing that absolute need for pristine purity against the huge environmental and economic benefits of maximizing the amount of recycled glass in the loop? Where does that balance point lie in the future?
That's a fascinating question. Something to definitely ponder next time you're looking through a perfectly clear window or tapping on your phone screen. Thank you so much for taking us through that incredible journey, and thank you for joining us on The Deep Dive.